Welcome to Astro 101, the Sun and its Neighbors. I'm Professor Bart Netterfield. Today is already Lecture 16. I can't believe how quickly the semester has been going. Today, we're going to be covering some really exciting things, talking about asteroids, comets, and the dwarf planets. And this is an area which is incredibly exciting because of all the really amazing research that's going on in this area in the last few years. It seems like every year there's new and exciting things being discovered. So even today, we'll be covering stuff that's actually been learned in the last month. It's amazing. So let's start out with the asteroids. Now, the asteroids are a group of objects that live in between Mars and Jupiter. There's a few of them that live along the orbit of Jupiter. They're kept there by Jupiter's mass itself, but most of them live in this band between Earth and Mars. And there are a lot of them. Here is a simulation of all known asteroids as of 2018. And you can see that most of them live here in between Mars and Jupiter's orbits, but there are a number of them that live in near Earth even. And we'll learn about the significance of that. But most of them live here in between Mars and Jupiter. Now, asteroids, like all objects, orbit according to Kepler's laws. And if you remember, in Kepler's laws, one of the facts is that objects orbit in ellipses, where the sun is at one of the focuses and the other focus is empty. The planets move in these ellipses, and they're slow moving out here, and they move in fast like this. It turns out, according to Kepler's third law, that the period, the amount of time it takes for a complete orbit, depends on this distance here, the distance from the center of the orbit to the edge called the semi-major axis. The time of an orbit, or the period, depends on the semi-major axis. So there's something that people noticed when they started plotting the position of all of these asteroids. Now, in this picture, you don't see any real trends. You see just kind of this band of asteroids starting in here and getting denser and denser and then getting less dense as you go out. It turns out that if instead of plotting the position, you plot the semi-major axis, and on this, so here's an interesting plot here. On this axis, we have the semi-major axis. So in AU, so the sun would be off in this direction. And the Earth would be at 1. So this is 2, out 2, and Jupiter's out in this direction. This is the number of asteroids that live at this distance in terms of the semi-major axis. It's not where they are right now, but this is the semi-major axis. You see that there's a bunch of asteroids that live here inside of this point. There's another group that lives here in between these 2 points, a group here and a group here. What's really interesting is that you see no asteroids that are this far away from the sun, no asteroids that are this far away from the sun, very few this far, and none this far. Now that is very strange. What is going on? What are these gaps? They're called the Kirkwood gaps. Well, it turns out that this distance here forms what's called a 3-to-1 orbital resonance with Jupiter. What is a 3-to-1 orbital resonance with Jupiter? We'll explain that in a second. This gap here is at 5-to-2 orbital resonances. Now, what is an orbital resonance? An orbital resonance, a 3-to-1 orbital resonance, means that the asteroid goes around 3 times exactly whenever Jupiter goes around once. So there are no asteroids that go around 3 times when Jupiter goes around once. There are plenty that go around a bit fewer times, a bit more times. There's plenty that go around a bit fewer times, but none that go around exactly 3 times when Jupiter goes around once. Similarly, there are no asteroids, or very, very few asteroids, that go around 5 times when Jupiter goes around twice. Okay, that's what we mean by an orbital resonance. Let's look at a little render, and we can try and understand an orbital resonance. So here we go. We have Jupiter orbiting, and then 2 asteroids. This asteroid's gone around once. This one's gone around once, so blue's gone around, pink's gone around once. There we have blue's gone around twice now. Pink's gone around twice. And now, whoa, here we go. Jupiter's gone around once, and blue's gone around once. So Jupiter and blue are in a 3-to-1 resonance. So here we are going, we're continuing to count up. 4, 5, and then finally, boom, we get to the end. Jupiter's gone around twice. Pink has gone around 5 times. Blue's gone around 6 times. So pink and Jupiter are in a 5-to-2 orbital resonance. Should we look at that again? Let's look at that again. So here we go. All 3 of these are orbiting. Blue has gone around once. Pink's gone around once. Blue's gone around twice. Pink's gone around twice. And now Jupiter and blue have gone around. Jupiter once, blue 3 times. Jupiter and blue are in a 3-to-1 orbital resonance. Now we continue counting up as these numbers come up, and we're gonna find in a moment when Jupiter gets to its end that Jupiter has gone around twice, while Pink has gone around 5 times. So Jupiter and Pink are in a 5-to-2 orbital resonance. Now, if you just set asteroids orbiting, they're probably not going to be in an orbital resonance. It's only special times that you get into an orbital resonance. Now, why is this interesting? What it turns out is that orbits in an exact resonance with Jupiter get displaced. Every time they go around, Jupiter gives a little tug on them. Jupiter gives a little tug on them. Jupiter gives a little tug on them. Every time they come around to the same place, which eventually causes the asteroid to move out into a different orbit. So most asteroids that are in a 3-to-1 or a 5-to-2 resonance get knocked out of that orbit into some other orbit. So we see these gaps. And this is the effect of Jupiter affecting how the asteroids orbit. We can look at this in a different way. Here, we're plotting the position of all the asteroids, except for instead of distance, we're plotting the semi-major axis. So we're pretending that they were all circular orbits. So if they were all circular orbits with the same semi-major axis, this is where they would all be. And you can see these gaps where resonances with Jupiter cause any asteroids with those orbits to be displaced. So you have these gaps. So this is the effect of Jupiter on the orbits of the asteroids. Well, what are asteroids? Well, in general, asteroids are these large, lumpy objects. Well, not that large. They're not large enough to be roughly spherical, and they're rocky, and they orbit the sun. That's what an asteroid is. We're going to look at them in more detail. Let's start then looking at the objects in the asteroid belt, starting with the largest one. The largest one is this object called Ceres. So Ceres is around 1,000 kilometers across. So I've got Ceres here hovering over Canada. Here's Toronto right here, in case you're wondering. And you see that Ceres is kind of, well, I guess it's, sort of the size of Ontario or something. It's about 1,000 kilometers across. And, well, you look at Ceres and this kind of looks like the moon, right? That looks like a boring, spinning rock. Kind of like we've already seen. We've seen the moon, we've seen Mercury. Ceres just looks like those. Now, it's smaller than the moon. It's smaller than Mercury, but it otherwise looks kind of the same. So here it is, high-resolution picture of it. Here's Ceres. The Dawn space probe spent several years, 2015 to 2018, studying Ceres, orbiting around it, taking high-resolution pictures of it. It's just ran out of fuel recently. This thing looks just like the moon or Mercury, except what's going on there? What is these bright white smudges? Let's kind of zoom in on those high-resolution images. They've studied these images, and the conclusion is that these are salt deposits from a cryovolcano. Let's think back to a few lectures ago. How would you determine the chemical compound of something? Remember? Remember spectroscopy, looking for lines? So one way you can tell the chemical composition of something is doing spectroscopy of it. So they've determined that these are some sort of salt deposits from a cryovolcano. So some kind of salty liquid is leaking up from the inside of Ceres and leaking out onto the surface and leaving these salt deposits. But that's weird. Like, you couldn't have that happen on the moon. Why couldn't you have that happen on the moon? Well, the moon has no water. It has no liquid lakes under the surface with salt deposits. That couldn't happen on Mercury because Mercury's completely dead. But here we have on Ceres, you've got these salt deposits leaking up. Now, another thing that happens is that, other thing's weird thing here. That's this 4-kilometer tall mountain on Ceres. Like, how did that get there? What is going on? This is very strange. Let's look at the wall of one of these, craters. And we see landslides, and we see more of this salt deposit stuff sticking out. So at first look, Ceres, you say, hey, this is just a rock. But when you start to study the surface, you start to realize there's some things going on that are not really like just a rock. Now, one of the things you can do is you can very, very carefully measure the orbit of a satellite orbiting the planet. The matter inside the planet, or the moon, will affect the orbit of your satellite. And from that, you can start to probe what's inside the planet. After all the studying they've done on Ceres, this is what they've concluded. And this is actually in the last couple of years. It's actually changed. This picture has changed slightly in 2 years, given better data. Now, this is still somewhat tentative, right? This is not, we don't know this for sure, but this is what the evidence looks like. It looks like Ceres has a rocky center, not an iron core, but a rocky center. It's got a liquid brine layer and then an icy crust. And this liquid brine can leak up through and cause these cryovolcanoes. This is really cool. It looks like the moon. It looks like Mercury. It looks like just a big dead rock. When you study it more carefully, when you study the gravity from an orbiting satellite, when you look at the careful pictures, you look at the materials being ejected, you discover that in fact, it is a very different beast. It's got a rocky core, not an iron core. It's got a liquid brine layer, and it's got a crust. So, Ceres, a very interesting object. It's not just a big rock. But there's some things about Ceres. So I want to just do a quick instant quiz question. Instant review quiz, kind of. And some of this is review, and some of this is actually thinking about it. So let's just think about this question. Why is Ceres nearly spherical? Why is Ceres nearly spherical? Let's go back over here. Let's imagine that you made a big bulge on Ceres. Let's make a big bulge here. What would happen to that bulge? Well, gravity is pulling the bulge down. And in fact, on Ceres, the force of gravity would be greater than the strength of the crust and even of the core. And so it would relax back into a sphere. What's going on here is Ceres is too massive. The force of gravity is too great to get the object to become significantly non-spherical. In fact, Ceres is right on the edge of it. It's about the smallest objects where gravity is going to win. It's called hydrostatic equilibrium. Basically, what's going on here is the force of gravity is too great for very large distortions from spherical to be maintained. Gravity is going to crush it back into roughly a sphere. So let's look at the instant review quiz. Why is Ceres nearly spherical? And I already just told you the answer, so let's see if you can remember it. Collisions of planetesimals that made Ceres came from all directions. That might be true, but I don't think it would make it necessarily spherical. Erosion. It used to have a thick atmosphere and liquid water on the surface. Well, let's think about that. Could that be true? Could Ceres have ever had a thick atmosphere? Now, if we think back to the previous lectures, what do you need to hold a thick atmosphere? Well, you need pretty strong gravity, otherwise it just escapes. Ceres has some gravity, but it's only 1,000 kilometers across. It's a lot less massive than the moon. It's a lot less massive than Mercury. So if the moon and Mercury can't hold an atmosphere, then there's no way Ceres could have. So this is almost certainly not true. Ceres almost certainly never had a thick atmosphere. It's large enough that the strength of gravity is stronger than the strength of the rock or ice it's made of. We think that's the case. We think it's D. And E, Jupiter's nearly circular orbit has rounded it off. That looks just like a question I had to stick an answer in there. That doesn't actually make any sense. Why would Jupiter's nearly circular orbit do anything to the shape of Ceres? It wouldn't. So the answer is C. Ceres is nearly spherical because the strength of gravity is greater than the strength of the rock. And so the rock cannot support a very large mountain. If you think about the mountains on Earth, they are as large as they can be. And in fact, they are shrinking. Just as they settle back into the Earth. The plates move, make a mountain, and then the weight of the mountains makes them sink back into the Earth. So the Earth cannot be much less spherical than it is. Same with Ceres. Ceres is can't be a whole lot less spherical than Ceres is because it's so massive. Okay, now, Ceres. Because Ceres orbits the sun, number one, because it's massive enough that gravity has made it roughly spherical, it's a planet. Ceres is a planet. It orbits the sun and it's mostly spherical, but because it's not massive enough that it mostly clears out its orbit, there's a whole bunch of other things sharing the same orbit as Ceres that are not wildly different in mass than Ceres, that we consider Ceres to be a dwarf planet, but Ceres is a dwarf planet. Because it orbits the sun and is massive enough to be spherical, it's a planet. Because it doesn't clear out its orbit, it's a dwarf planet. So there we go. Ceres, the smallest of the dwarf planets. It's also the largest object in the asteroid belt. So after Ceres comes the object called Vesta. Now Vesta, as you can see, is around half the size of Ceres. It's around 500 kilometers across, so sort of, kind of the size-ish of the Great Lakes region. Vesta looks different than Ceres. You can see it here in relative scale. The moon, Ceres is a lot smaller than the moon. And then finally Vesta, which is smaller than Ceres. Vesta is the largest asteroid. It's around half the size of Ceres. It's not really round, so we don't call it a dwarf planet. To be a planet, it needs to be good and round, and Vesta really isn't good and round. Therefore, we don't call it a dwarf planet. We call it the largest of the asteroids. I mean, you could say, well, maybe it's round enough. No, we're going to say it's not round enough. But these are just names. So if you really want Vesta to be a dwarf planet, you can have an argument with the IAU. In the meantime, we'll call it the largest of the asteroids. What do we know about Vesta? The Dawn space probe explored Vesta in 2011 and 2012. And it spent a lot of time taking pictures, orbiting it. There's lots of crazy stuff going on with Vesta. It got these weird striations. It's got, on the South Pole here, it's got an absolutely enormous crater, almost the size of Vesta, which is kind of causes its weird squat nature. Dawn orbited Vesta for a couple of years, very carefully probing out the gravitational fields, trying to understand the internal structure of Vesta. And what we find with Vesta is very different than Ceres. Vesta doesn't have that brine layer. Vesta has a nickel iron core. It's got a mantle made of a mineral called olivine, and then a crust floating on top. Now, this is what's called differentiation. I guess you've learned about that back in lecture 12. Differentiation happens. What this means, basically, is at one point, Vesta was hot enough for the interior to become liquid. This is what's called differentiation. So I've got a special guest who's going to give us a little demonstration of differentiation. Joel, what do you got going on?
I am preparing a demonstration
of differentiation.
Exactly. It is when heavy stuff will float to the bottom and lighter stuff will float to the top.
Okay, so what we're seeing here is the same picture as with Vesta. We've got the iron core here in the bottom, we've got the olivine mantle, and we've got the crust floating to the top. So this is basically, anytime then you've got a planet which has become liquid, you're going to get this differentiation happening.
Cool.
Well, thanks, Joel. Appreciate it.
You're welcome.
So at one point, Vesta was hot enough for the interior to become liquid. Consequently, Vesta experienced differentiation, and it has this nickel iron core, a olivine mantle, and then a rocky crust. Very cool. All right, instant review quiz. Which of the following is the main distinction between an asteroid and a dwarf planet? What's the main distinction between an asteroid, like, say, Vesta, and a dwarf planet, like, say, Ceres? What's the main distinction? Orbital eccentricity. Shape? Age? Orbital semi-major axis? Or the number of objects sharing the same orbit? What's the main difference between an asteroid and a dwarf planet? Well, the orbital eccentricity doesn't really make a difference whether you call it a dwarf planet or an asteroid. There are dwarf planets with very high and very low eccentricities. There are asteroids with high and low eccentricity. So it's not that. Shape. That's the one. To be a dwarf planet, you have to be basically spherical, but that comes from being large enough. I think if I just threw a basketball in space, we wouldn't call it a dwarf planet because it wasn't gravity that made it spherical. But when gravity forces it into a spherical shape, then you can say it's a dwarf planet. Age doesn't make a difference. They're probably very similar ages. Orbital semi-major axis, well, they're different between Vesta and Ceres, but that doesn't really matter. You can have asteroids that are further away than Ceres and closer than Ceres and vice versa. It doesn't really matter. Number of objects sharing the same orbit? Nope. That might be a difference between a dwarf planet and a planet, but it's not the difference between a dwarf planet and an asteroid. So the answer here is shape. If gravity has forced it into a sphere, it's a dwarf planet. If it has not, then it is an asteroid, or maybe a comet, as we'll see later on. Okay, moving on. So we've looked here at Vesta, sitting here over the Great Lakes. The next largest object that we're going to talk about, and now we're getting into where there are a huge number of objects of this size. The next one we're going to look at, just because, is an object called Eros. Eros is now about 34 kilometers across, quite a bit smaller than the previous things we were looking at, which were around 500 kilometers across. So you can see Eros compared to the Greater Toronto Area. So Eros and the GTA, kind of similar sizes. So this is another object in the asteroid belt. Eros was visited around 2000, so actually quite a long time ago now, by the Near Shoemaker spacecraft. It made gravity measurements, but by orbiting it, they observed the surface. It's got cratering, so it's got a very old surface. It's been cratered. The gravity measurements indicate that Eros is homogeneous. It's not differentiated. It's kind of the same density all the way through. So this is just a big, boring rock. It's not differentiated. It's not got an iron core. It hasn't got a rocky crust or anything else. It's just kind of this big rock. It's thought that Eros was probably kicked out of some larger object in some collision. But there it is. And this is one of a huge number of objects around this size. Now, this particular one is in an orbit where it has about a 50-50 chance of striking the Earth in the next billion years or so. So not next month, but it's pretty likely that someday Eros might strike the Earth, which would be bad, as we'll see. Okay, that's Eros. This is kind of these intermediate size asteroids in the 10 to 50 kilometer range. They're typically undifferentiated rocks, at least if Eros is like them all. But I'm sure that they're all different. Who knows? All right, let's go even smaller. Going from Eros, which was kind of 30 kilometers across, down to a really cool rock that has just been studied called Bennu. This is Bennu. Bennu is about a half a kilometer across. So we have it here compared to U of T campus. So here's Con Hall. Here is some buildings. My lab is over here in the corner. This is the physics tower. Okay, so here we have Bennu orbiting. Well, what do we know about Bennu? Well, Bennu is very close to Earth. It actually has a much higher chances of colliding with the Earth. And so there was an experiment that was launched a couple years back to go and study it. And so it was launched, and this small satellite called OSIRIS-REx managed to actually get into an orbit around this really tiny asteroid. It is the smallest object to ever have been orbited before. And here's what we saw when the satellite got to Bennu. It looks like this really rubbly pile of rocks. I mean, look at this thing. It's just this kind of blacky gray blob of rocks. This is a kind of big one, right? This is, tens of meters across, but still, it just looks like kind of a mess. Not just one rock, not the sort of thing we saw with Eros, which just kind of looked like one big molten rock. This looks like lots of rocks. This one here happens to be made of magnetite, which is a material that you can use for magnets. Got iron content in it. Again, how did you figure that out? Well, with spectroscopy, right? So what is this thing? Now, one of the really cool things there's a couple other odd things that were seen about Bennu by OSIRIS-REx as it orbited. One of the things it saw is that at one point, a bunch of little rocks and gravel got spit off of Bennu. Why? Something happened, something shifted, and boom, a whole bunch of rocks got spit off into space. Now, this is really convenient because they can now track these little rocks as they orbit Bennu, as well as tracking OSIRIS-REx, and tracking these particles and tracking the spacecraft very carefully. They were again able, using the gravity on these objects, to probe the interior of Bennu. They discovered a couple things. Number one, the density of Bennu is very low. It's much, much lower than the density of rock. So it's probably quite porous, like it's not tight. It's almost the same density as water. So it would not float, but barely not float, which is a weird thing if it's made of rocks. It also appears that it might actually have some large hollow caverns in it, like 100 meters across. And this is for a 0.5 kilometer type object, like some big hollow caverns inside of it. That's not certain. It may not be true. It fits the model, but so do other things. But what is certain is this object is very low density. It's very porous. It's not homogeneous. The density varies around it, across it. It's not just a big rock. Now, one of the really cool things they wanted to do with OSIRIS-REx was actually try and go and land on the planet, on the dwarf planet. And here you have OSIRIS-REx in a render. It's not real. In a render, come in, land on it, blow out some nitrogen to stir up some of the rocks, and then grab a sample into this machine, and then return the sample back to Earth to study the rocks. So just really quite recently, I guess it was on October 20th, so not even a month ago when I'm recording this, OSIRIS-REx, this is OSIRIS-REx approaching Bennu to try and take this sample. So here it's coming in, and we're looking at the rocks getting closer and closer and closer and closer. And just look at this ground. It's just a mess of gravel and rocks and dirt and sand. It's just, what is this thing? And we're getting closer and closer and closer. And pretty soon now we're going to see the shadow of the grabber. We're getting closer and closer and coming in and coming in. There's the grabber coming in. It's going to be just out of the picture. Whoa, the blast of nitrogen. And what happened there? It ejected the nitrogen, and it just kicked up this enormous cloud of rocks and gravel. And OSIRIS is not really an object. It's kind of a pile of gravel and rocks and boulders, kind of loosely held together with gravel. So when OSIRIS went in to try and grab a sample, it just, well, it blew stuff everywhere. Now, that's fine. It managed to get a really good sample, more than they were hoping for even. And the sample is on its way back. But it turns out that this, here is some cool pictures. There they are, putting the sample thing into the sample return container and closing it up. And now it's ready to come back to Earth. This is a heat shield here. This is going to make a re-entry into the Earth and land somewhere where they can pick it up and take the samples back for study. So it turns out that Bennu is well, it's not really a rock. It's a pile of gravel and dirt and boulders and whatever, just kind of held together by gravity. Gravity's not strong enough to compress it, not strong enough for differentiation. It never really got hot enough to do anything. It's not even hot enough to make a rock. It's just a loose pile of gravel. Well, that's pretty great. That's kind of a weird thing, a 0.5 kilometer across pile of gravel. All right, so the orbit of Bennu crosses the Earth's orbit. And it sometimes gets very close to Earth. And every time it does, its orbit gets perturbed into a different orbit. And then it comes past close to Earth and gets perturbed again. Consequently, it's very hard to predict well into the future what Bennu's orbit's going to be. But we can make some odds about what Bennu's going to do. There is a 1 in 2,700 chance that Bennu is going to strike the Earth before the year 2199. So sometime in the next, 180 years, 179 years, okay, 200 years, Bennu has a 1 in 2,700 chance of striking the Earth. And just in terms of, trying to evaluate those odds, those are the kind of the odds that someone in their 20s has of dying of COVID. So, yeah, seems like a low chance, but sure ain't zero. And Bennu is just one of a huge number of asteroids. So That's a thing to worry about if you want to. There are asteroids out there, and they could strike the Earth. Now, this is a 0.5 kilometer across asteroid. We'll see in a few minutes just how important a 0.5 kilometer asteroid strike would be. So coming back to it, here we have, there's around 25 million asteroids larger than 100 meters in diameter. 25 million asteroids bigger than 100 meters in diameter. Yikes, that's a lot. Now, you've probably seen in movies, maybe like Empire Strikes Back or something. I'd love to show you the clip, but, you know, copyright and all that stuff. But you've seen in movies and things, spacecraft traveling through asteroid belts. And they're dodging the asteroids and making around. They're all flying around and bumping into each other. So I was like, well, that's kind of cool. So I thought I would show you a more realistic simulation, a more realistic simulated video of what it would really look like to travel through the asteroid belt. So here we have this video here of what you would see traveling through the asteroid belt. Now, I should note that I didn't include the background stars. So I could put the background stars in, but I didn't do that. This is just the object in the asteroid belt. And here we are traveling through the asteroid belt. And this is typically what you would see as you traveled through the asteroid belt. So let's give it a bit here so we can really see what we're... Okay, you don't see anything. That's because even though there's like 25 million asteroids 100 meters in diameter or larger, their space is so huge, they're so far apart, that you would not typically expect to see one from another. So traveling through the asteroid belt, you're not going to see any asteroids. You're not in any risk of hitting one. That whole thing in movies where you have them all close and bumping into each other, that's just fun movies. In fact, it's worse than that. Think about it. If you had all those asteroids in, say, an Empire Strikes Back or some movie like that where you have all the crowds of asteroids, what's gravity going to be doing to them? It's going to be pulling them together. That cloud of asteroids would get pulled together to form a planet pretty quickly. So it wouldn't even work. But instead, the real asteroid belt, pretty boring. It's really, really empty. Okay, so we've talked about the asteroid belt. This is this cloud of something like 25 million or more asteroids, 100 meters in diameter and larger. There's a lot more less than 100 meters. I'm only talking about the ones 100 meters in diameter and larger, 25 million of those, orbiting the sun, mostly between Mars and Jupiter, although there's some that come right down in close to the Earth. If you go out, well past the orbit of Neptune, you get another belt of objects. So in here was the asteroid belt. Out here is another belt of objects called the Kuiper belt. It's 20 to 200 times more massive than the asteroid belt. Now, we don't know. It's really, really hard to measure these things, as we'll see in a minute. But there's a lot of stuff out there. 20 to 200 times more massive than the asteroid belt. It includes several known dwarf planets. And we expect that there's many more that we haven't detected. And all these objects out here formed outside the frost line. So we expect them to have rather different compositions. Most of the asteroids are made of rock. Ceres is weird because it's got this brine layer to it. But most of the asteroids are just made of rock. Things forming outside the frost line, all these things, they're going to have not just rock, but also ices. In fact, it's so cold out here, we can expect things to be made of things that on Earth would be considered gases. So we're going to see that. Formed outside the frost line. My favorite, everyone's favorite Kuiper belt objects, everyone's favorite dwarf planet, I think, because it's so cool, is Pluto. And so back in the 2000s, they launched New Horizons. It took a 9.5-year trip to get to Pluto. 9.5 years. The fastest object, besides like a particle, but the fastest macroscopic object ever made was New Horizons. It was traveling at 50,000 kilometers an hour when it left the Earth. It took 9.5 years to get to Pluto. That's traveling the fastest that anything's ever been launched. So launched from Earth, comes by Jupiter, comes by Saturn, and makes its way out to Pluto. Okay. What did it see? Here is the picture of Pluto. Pluto is, well, let's look at some of the things we can see from Pluto here. First of all, it's pretty much spherical. That makes sense. It's like 2 or 3 times larger than Ceres, it's definitely large enough that gravity can collapse the shape and make it roughly spherical. It has, on its surface, it has regions with craters, right? So this part of the surface is very old. It's been unchanged for billions of years. But then it's got this region here with no craters. That's cool. If you look it up close, it's this, turns out this material here, the surface, nitrogen. Well, what's nitrogen? Well, nitrogen is what like 3/4 of the air is made of. Nitrogen gas. It's nitrogen gas. Now, it turns out if you take nitrogen gas and get it really cold, somewhere around, minus 200 degrees below 0 Celsius, nitrogen becomes a liquid. Okay? If you get it even colder than that, nitrogen becomes a solid. This material here is frozen nitrogen. What on Earth is the air, the gas, it's so cold on Pluto that what's on Earth is a gas, on Pluto is a solid ice. You can walk on it. Now, it apparently has melted since the last craters landed. Makes sense. It melts at a very, very low temperature, but somehow Pluto got close enough to the sun or something that this material melted sometime in the last, don't know how long. Very, very cool. These right here, these are water ice mountains. And most of this surface over here, where you have all the craters and stuff forming that's stronger and older, that's probably water ice. So you have water ice mountains and nitrogen ice plains. Pluto is really cool. Pluto is different. It's a weird place. Imagine standing on this surface. Now remember, this becomes a gas at something like 200 degrees below Celsius. So if the warmth through your boots would probably warm the ice up, so the surface you're standing on would become a gas. That would be weird. So I don't recommend ever taking a vacation on Pluto. It's awesome to look at. It would be an amazing challenge to try and make a robot that could travel around on Pluto. How would you do it, right? You'd have to keep the robot at cold enough that it didn't melt the surface and turn it into a gas. But electronics can't work that cold. So yeah, we may never actually be able to visit there and drive around, even with a robot. It's a really cool place though. Cool as in really cold. So this spot right here is a spot right there on Pluto. There's other weird things on Pluto, like look at this stuff. What's going on here? It's some of these weird rills. Like somehow the material has evaporated in some really strange way. Pluto is different. It's really cool. It's very strange. Pluto, as you remember, also has a large moon, Charon. Compared to Pluto, Charon's a very large moon. The surface is more craters than Pluto. There's craters all over it. The surface is mainly water ice. So Charon, Pluto, kind of similar, but not. I mean, here they are, two objects orbiting each other, and they're actually different. So it's pretty cool. Pluto's orbit is in a resonance, a 3-to-2 resonance with Neptune. Pluto goes around 3 times. No, Neptune goes around 3 times, and Pluto goes around twice. And so they always pass by each other at the same spacing. Now, sometimes a resonance will kick something out. Sometimes a resonance will make it more stable, depending on where you are, what phase you're in. This is a resonance where the resonance of Pluto with Neptune keeps Pluto's orbit stable and makes sure that Pluto can never run into Neptune. Whenever Pluto crosses Neptune's orbit, it does so when Neptune is not there. And that will always be true. So even though Pluto is crossing Neptune's orbit, Pluto and Neptune will never collide. Orbit is inclined. Inclined is not in the ecliptic. All these guys are in the ecliptic plane. Pluto's orbit is inclined, which means it has some kind of slightly different history. And so this is Pluto. Pluto's, I think, pretty cool. Now, Pluto happens to be the largest object in a family of these objects that were formed well outside the frost line. These are objects which are mainly made of ices. And what the rest, these objects have been known for a long time, but people didn't really know what they were. These objects are called comets. Now, these objects called comets appear in the sky rarely. I mean, every few years you might see one. Or sometimes even, like the really impressive ones, are even every few decades. When they show up, they're visible for days. Like don't picture something like streaking across the sky. It's sitting here, and then tomorrow it's here, and then tomorrow it's here, and it, drags across the sky quite slowly. They have tails pointing roughly away from the sun. There's a dim tail, which points exactly away from the sun. This kind of light blue one, you might be able to see it here on the screen. And this brighter one, which kind of points back away. The comet is actually moving in this direction, and so it's pointed back away from the direction of the sun. And these objects often come back on a fixed period. So it might come through, and then 12 years later, come back again, and then 12 years later, come back again. Or it might be one that comes back every 100 years, or comes back every 900 years. So these comets, different comets, come back at different fixed periods. Many of them do, not all of them. So what is going on? What's going on with a comet? A comet, first of all, clearly, if it's coming back and coming back and coming back, is an object in an elliptical orbit, a highly elliptical orbit, where it's going very slow out here, scoots in, speeds up, and then slows down again. Scoots in, speeds up, and slows down again. Okay? It's really cold out here. This is a long way from the sun. Could be out well past even the orbit of Pluto for the really, really slow ones. Really cold out here. Quite a bit warmer in here. As the object comes in, the sun heats up the comet. If it formed out here where it's really cold, and then something bumped it to make it go into this elliptical orbit, if it formed out here, then it's got a lot of ices. Think about Pluto. Pluto made of nitrogen, which out there is rock, and inside near where the Earth is, it's a gas. So it comes in, and the sun heats up the comet, and the ices melt and boil away. And you get this stream of material spewing out of the comet. Cool, but why are they pointed the way they point? So it turns out that what happens is that this path right here is the path that the comet is following. The sun is down here. Sunlight comes, it warms up the comet, and the gases spray off the comet. And then the sunlight pushes on the gas and the plasma and makes it fly away, directly away from the sun in the direction of the solar wind. The dust also gets pushed on, but it's getting pushed on by light pressure, not as hard, and so it isn't going as fast because the comet is going this way. The dust trail tends to tail behind it. Then you get larger particles, chunks and stuff falling off that kind of litter the orbit of the comet. So the comet is coming in, it's spewing off gas, which makes a gas tail. It's spewing off dust, which makes a dust tail, and spews out little particles, which end up along the orbit of the comet. So what does a comet look like? Because what we're seeing out here is this glowing thing. If you get in right close to a comet, that was something people really wanted to do. It was very exciting. They started actually being able to take missions to comets in the last decade or two. In 2015, Comet 67P was visited by the ESA Rosetta space probe. Here is a picture of Rosetta. You can see the gas blowing off of it. You can see this weird structure. It's got holes and stuff in it. What's going on there? Maybe that was the shape when it was made. It could be that's where the gas is left, and all you get left, this is like the rock being left behind. Hard to know. This is pretty cool. So when you look at this picture, you see something that's not quite realistic. When you look at this nucleus of the comet, it sort of appears that the comet is kind of a gray and black, well, gray and white color. That is actually not quite accurate, which is something I want to explain here. So I want to demonstrate a kind of an idea. And first of all, I want to visit one of our special guests for today. Let's see. So where is he? Where's our guest on the suitcase? Oh, look at that. It's Vader. Hi, Vader. How are you doing? Vader, what's wrong with that picture? Are you going to tell me? No. Vader's just going to hang out, hiding a black cat, hiding on a black suitcase, making him rather hard to see. Huh. Okay, Vader. Well, we'll talk to you later. Enjoy the suitcase. We have another guest. Deborah Ann you have a couple guests with you today here.
I do indeed. So this is Harry and this is Marco.
Hey, Harry. Hey, Marco. They look rather different.
They are different. So the reason that they're different is because they have different albedos.
What's albedo?
Albedo is the reflection of light coming from an object.
Ah, so more light reflects from Harry than reflects.
Absolutely, it does indeed. And even if you take a picture of Marco and Harry, Marco will barely show up, and Harry will show up in the frame.
Oh, okay, that makes sense. And this must also apply to planets and asteroids. Well, thank you very much, DA.
You too.
So, here's what's really going on. Here is a picture, for example, of, this is a picture of what, Comet 67P? This is the picture that you normally see. This is the picture of it as it would actually be. And I bet you can't even see it. That's because comets are actually almost perfectly black. There's only 4% reflection from a real comet. So here, the exposure has been cranked right up so you can try and see the comet. But in real life, if you just looked at it, it's almost perfectly black, like black paint. It's the reflectivity of a comet like 67P is a little bit lower, but very close to the reflection or the albedo of black paint. So we can look at here at some different representative objects. Here is the most reflective object in the solar system, Enceladus. It's almost got the same reflectivity of a piece of white paper. Here's the Earth, which is maybe a third of the light gets reflected. The Moon is actually quite dark. It's only reflecting around, 13-14%. And then here is a comet. The comets are incredibly dark. This is true for the comets. This is also true, incidentally, for Bennu, that really cool asteroid we were looking at. Its reflectivity, it's black, black, black. Its albedo is incredibly low. It makes these comets and asteroids, in fact, very challenging to detect because they are so dim. So one of the ways you can detect them, of course, is to have just really sensitive cameras. Another way is to try and look for when an asteroid passes in front of background stars. This is how they've actually detected some asteroids out even in the Oort Cloud. So it's pretty cool. When you think about these comets, you often think about them as being this kind of bright gray color. That's not the case. They're in fact very, very dark. They have very low albedo. Okay, moving on. What makes the difference between a comet and an asteroid? Well, it's the composition. Comets formed way outside the frost line. They're made of a lot of ices. Ices like nitrogen ice, which becomes a gas when it gets close to the sun, water ice, other volatile materials. Asteroids formed inside the frost line, mostly made of rock and other things that can stay solid or liquid when it's inside the frost line. So the composition, it tells you whether or not you've got a comet or an asteroid. If it's formed far outside, it's going to be a comet. If it was formed in close to the sun, inside the frost line, inside the orbit of Jupiter, it's going to be a asteroid. So that's the difference. So we've talked about the asteroid belt, which lives in between the orbit of Mars and the orbit of Jupiter mainly. Then we went out and we talked about the Kuiper belt, which is where all these comets live and are coming from. And even outside the Kuiper belt, there's some other objects. Sedna is an example of one of these dwarf planets. Sedna is orbiting well outside the orbit of Neptune in a highly elliptical orbit. We go even further than that, and we come to another cloud called the Oort Cloud. The Oort Cloud is this roughly spherical cloud of comets that exists well outside the Kuiper belt, well outside even the orbit of the known dwarf planets. It's called the Oort Cloud. There are trillions of objects in the Oort Cloud. It is an enormous reservoir of comets. These were kicked out by gravitational interactions by Jupiter and Saturn. So, kind of amazing. And some of the really long period comets are coming from the Oort Cloud. Maybe they'll interact with each other and one will get sent in on an orbit toward the sun. Boom. And we'll see this comet that shows up and then leaves again. So the Oort Cloud. We've got the asteroid belt, we've got the Kuiper belt, and then way outside, way out here, is the Oort Cloud. The Kuiper belt and the Oort Cloud contain comets because objects out there would have formed outside the frost line. They have a lot of ices in them. Inside the frost line, the objects there are asteroids made of rocky materials. There's one more very relatively rare type of object, and these are objects that come from interstellar space, not from our solar system at all. A couple of years ago, 2018 in fact, an object from well outside the solar system came whipping in, got close to the sun, bent around the sun, and it went shooting back out again. Its name is Oumuamua. It's kind of a cool name. I wish I could pronounce it. Came from interstellar space and then left again. It's probably a comet or an asteroid kicked out from some other solar system. Like it was something got kicked out and it didn't end up in that solar system's Oort cloud. It got sent out into interstellar space and has just traveled now for a very long time before coming skirting through our solar system, nearly getting close to our sun and then shooting back out again. This object is a few hundred meters long. It's similar to the size of Bennu, right? A few hundred meters. Just a random object. The thought is that there's a very large number of these because a lot of objects get kicked out of their home solar systems and they just fly through space. And then very occasionally they might come across another star like this one did, shot around the star and then headed back out again. So, pretty cool. All right, another instant quiz. Which of the following is the main distinction between an asteroid and a comet? What is the most important distinction between an asteroid and a comet? Is it orbital eccentricity? Okay. Is it the shape? Is it their age? Is it their composition? Or is it the number of objects sharing the same orbit? Okay, so think about orbital eccentricity. That's whether it's kind of circular or an ellipse. Well, most of the asteroids have a relatively circular orbit, but there are some comets who just live out in the Kuiper belt who have very circular orbits too. So it's not orbital eccentricity, although there are some comets with very eccentric orbits. That's not what makes them comets. What makes them comets is not that. The shape of the objects? No, I don't think they're indifferent at all. I mean, there's nothing about the shape that tells you if it's a comet or an asteroid. The age. Probably all formed at the same time, so not the age. Composition, that's the one. Formed outside the frost line, it's made of ices. It's a comet. Even if it never comes in close to the Earth, you still call it a comet. If it stays out there and never gives off a tail or outgasses, we still call it a comet because it's staying out, because it's made of ices. If it's formed inside the frost line, it's made of rocky materials. So it's the composition. Number of objects sharing the same orbit. That tells you if it's a planet or a dwarf planet. That's not the topic here. So the answer is composition is the thing that's the main distinction between an asteroid and a comet. Asteroid and a comet, the main distinction is whether it's made of ices or rocks. So let's go back to this again. 25 million asteroids larger than 100 meters in diameter. There's a lot more asteroids that are smaller than 100 meters in diameters. A lot more. In fact, every night, millions of objects strike the Earth. Millions, every night. Now, most of them are like small, like a grain of sand, and they just burn up in the atmosphere. Some of the larger ones, like peas, come streaking through, and you can see these beautiful trails. If you've ever been out on a really dark night and you just wait, you can see these shooting stars, they call them. It'd be some small pebble or a pea or something that's hit the atmosphere and make a beautiful streak of light across the sky as it burns up. It's going so fast that the heat of slowing down in the atmosphere just melts it and becomes a gas. Millions of these strike the Earth. When the Earth goes through the tail of a comet, when the Earth goes through the path of a comet that's gone through, you can get a lot of these things. Because remember, he said the comets give off little pebbles and bits of sand and stuff. So as the Earth goes through the path of a comet, you can get these things called meteor showers. And these would be little bits that have fallen off a comet that's been whipping through. So every night, millions of objects strike the Earth. Most are very small, burn up in the atmosphere. But sometimes they actually hit the Earth. Here's an example of a asteroid that landed in the desert. Here's one that is a very large iron asteroid. Some of the asteroids are actually from the cores of planetesimals that had differentiated and then got smashed together and broken up. So you get some of these large iron asteroids. Some of them are just made of rock because they were from the mantle of an asteroid that got destroyed. And sometimes they're just the natural pieces, who knows where they came from, that come whipping in. Sometimes very large ones hit the Earth. This 50,000 years ago, a 50-meter asteroid, or comet, we don't know, it was an asteroid, we know it was an asteroid because it was iron, hit the desert in Arizona. This is at Meteor Crater. This is a 50-meter object made this giant crater. Bennu is 10 times larger than this. So yeah, this could be bad if we get hit by a meteor. It's not entirely irrelevant. It's not super likely. It doesn't happen that often, but it does happen. Maybe we should worry, maybe not. Maybe worrying can't help. I don't know. Now, Susan and I were out off on a trip recently, and we went to a dinosaur museum, and we saw all these wonderful dinosaurs. The fact that we're not running away screaming and not eaten indicates that they're not actually real. But you can ask this big question: how did these things become these? About 60 million years ago, the dinosaurs, which had been the dominant large life form on Earth for millions of years, all died out. All very, very suddenly. What happened to them? Well, it's the topic of this lecture, isn't it? 66.038 plus or minus 0.049 million years ago, an asteroid, or maybe a comet, something large, something around 30 kilometers across, that's like the size of Eros that we talked about before, struck the Earth down in here. So you can see the crater left in the ocean. It struck the Earth and caused giant clouds of dirt, blocked out the sun, changed the climate, and wiped out the dinosaurs and most species on Earth. A mass extinction. Our ancestors managed to survive, but it wiped out a huge fraction of the Earth, this one strike. So this happens, and it happens kind of every few tens of millions of years. You get one of these giant strikes that hit the Earth and kills most everything. It's happened numerous times. It's, I guess, a very important part of how evolution works. You don't want to be here when it happens. Not something we really know what to do about. You can worry about it. You cannot worry about it. Probably not going to happen tomorrow. All right. This was the great extinction event that wiped out the dinosaurs. Okay, one last quiz. Last instant review quiz. This is not really instant reviews quiz. This is a kind of a think about it quiz. This is something I want you to be able to think about, just basically from what we've done so far. Look at this picture. Here we have a picture of an asteroid. It's in pretty good focus, pretty good detail. How was this picture taken? Powerful telescope on Earth. A powerful telescope in Earth orbit. A spacecraft flew by it, or it was a computer reconstruction from radar imaging. It turns out you can actually take pictures this way, but they're not very good resolution. So this is too good a resolution for that. People have pointed large telescopes at asteroids, but the distances are so large, and these are so far away, and they're so small, that a telescope in the vicinity of the Earth, even one in space, cannot get a picture this clean. The answer is a spacecraft flew by it. Anytime you see a high-resolution picture of a asteroid, somebody sent a probe there to fly by it and take a picture. And these trips take a very long time, cost tens of millions of dollars to do, but super cool and interesting. So we have just done a lightning tour through the asteroids, the comets, and the dwarf planets. And I didn't mention there's a whole bunch more dwarf planets besides Ceres and Pluto. They're further out than Pluto. We know almost nothing about them except what their orbit is and how much they reflect. So we don't really even know what they're made of or what their surface properties are. We know almost nothing about them except that they exist. So I didn't really talk about them. We think there's a lot of them out in the Kuiper Belt. Besides that, though, we're really starting to get a handle on this amazing zoo of different objects that exist in our solar system. The different kinds of asteroids. Rocky ones, piles of gravel, ones made of metals, Ceres with this kind of brine thing, the dwarf planets and the comets made of ices. It is a fantastic solar system, a lot of great stuff going on. Anyway, hope you guys have a great week, and we'll talk to you next class.